Last week, we spoke about TensorFlow, homework number 4, regression and classification, and we started talking about the metrics for performance evaluation. If you have multiple types of algorithms, then how do you choose which algorithm is better? So today, we'll continue our discussion on the classification metrics, and then hopefully we will spend time on the next major machine learning algorithm, which we'll discuss, which is outside of the neural networks, which was decision trees, and also hopefully random forests, which are based on decision trees. So just a quick review of the last homework. These were the slides that we used last week. We talked about cross entropy and then popular classification techniques. And we'll talk about decision trees today, and hopefully also about random forests. And then we'll try to talk about some of the other ones in the next 1 or 2 lectures remaining. So in the last lecture, we spoke about what is called the confusion matrix. So this particular matrix is referred to as the confusion matrix. Why? Because it's kind of confusing as well, right? So you have the predicted class over here, and the predicted class is true in the top, is positive in the top row, okay, which basically means what you're predicting is positive, okay? Now, some of those may be true, and some of those may be falsely positive, okay? But this row is the positive prediction. The bottom row is basically the negative prediction. And in this case, over here are the true negatives, which are correctly predicted. And these over here are the falsely predicted, okay? So, and we looked at the following example, and I've labeled these as case 1, 2, 3, and so on. And so this was the first example that we looked at, where we saw that there were a total of 10 items, and 6 of them were rectangles, 4 of them were triangles, and we looked at various metrics. So the first thing that we looked at was accuracy, and we said that accuracy is basically the total positive plus the total negative divided by all 4 of them. Okay, so all the instances that we have. And then we said that this may be a problem, so this may not be a very good metric. So let's try to see if we can get a better metric. So this was the example where if you shift the decision threshold to one extreme on the right, as far as the rectangles are concerned, so all the rectangles are coming out to be true positives, okay? So, but the problem there was that the rectangles were, the triangles were totally miscalculated, okay? And we saw that over here, that even though the rectangles were doing well in this case, which is shown over here, the rectangles are doing well. The accuracy is also coming out to be very high, 96%, and the precision recall, which was the two additional metrics that we looked at, they were coming out very well for the rectangles. However, because we had shifted the decision threshold to one extreme side, the precision and recall for the other category, which was the triangles, was coming out really bad. Okay, and then what we did was we looked at the 2 cases, the 2 examples of the 2 cases, and we started looking at the trade-off between precision and recall. Okay, so this was the cases that we saw in which we tried to look at the 2 extreme cases. So this was the case where we tried to say, well, let's make the precision for rectangles much better. Okay, so to make the precision for rectangles better, we move the decision threshold towards the rectangles. And so there are only 2 cases over here left. And what it's basically saying is that the positive cases only have the rectangles, and so the precision over there is 100%. Okay. However, the recall comes out to be really bad, because now we're leaving out a lot of the actual rectangles on the other side. Okay. And now if you want to make the recall better for rectangles, we can move the decision threshold to the other extreme. And then what happens is that the recall becomes a lot better for rectangles, However, then what happens is that the precision suffers. Okay, so you can see that the precision has suffered, has gone down from 100%. Now we have a couple of triangles coming in into the positive side, and so the precision has suffered. Okay, so clearly there's a trade-off between where you put the decision boundary. Okay, and so so that's one of the issues that we can see is a problematic case, that if you go into the two extremes, one or the other starts to suffer. All right. So in one case, the precision can be really good, but the recall suffers. In the other case, if the recall becomes really good, the precision suffers. Okay. So one of the ways that you can address this is, and let's think about it. Can you think of a way that we can address this? So basically what we're saying is that here is a scenario and you really need to figure out what's the best boundary. Okay. And you can see that there's a trade-off. Okay. So even though the accuracy is remaining the same, so if you look at the accuracy in all of these cases, so this was the basic starting point. The accuracy is still 80%, regardless of whether you put the decision threshold in the middle, or you move it to the left, or you move it to the right. Okay, you can see that the accuracy remains the same. Okay, but the other parameters, the other metrics are changing. The recall and the precision are changing. So the question now is that, can we somehow combine these two techniques, all three of them? But accuracy is not really important because accuracy remains unchanged. But how can you combine precision and recall such that you get, so it's sort of like optimization. Okay, you're trying to find an optimum criteria which is combining two criteria which are, opposing each other. Okay, it's like saying for students, for example, think about CGPA and extracurricular activity. Okay, so you can see that there's a trade-off. If somebody spends too much time in extracurricular activities, their CGPA goes down. But if there's too studious and their CGPA goes up, then their extracurricular goes down. Okay, so somebody who's trying to recruit you, how do they combine these two things? Okay, if they look for one, the other suffers. If they look for the other, the first one suffers, right? So how can you combine these? Can you think of a way of combining both of these criteria such that you get the best of both? Okay, and you can think of very simple ways to combine them. So you could average them, right? So that's the basic way. You say, okay, what's the average of the CGPA and what's the average of the extracurricular activities? And you get something which simply says that you could have recall plus precision, and you take the sum of the two and you divide by 2. Okay, that's very good. However, what's the problem with this? If you think about the problem with this algorithm, is that suppose that one of these is really high. Okay, the recall is doing really well, but the precision is 0. So one of them can actually dominate the other. Okay, but you're looking for a balanced person. Okay, you're looking for somebody who's got both recall and precision involved. So is this going to solve the problem? Averaging the two? It's not, right? Because somebody who has 100% over here, 1 over here, and a 0 over here, all right, this comes out to be 0.5, is the same as somebody who's got, let's say, 0.5 plus 0.5, 1 upon 2, which is also 0.5, right? But you don't want somebody who's completely imbalanced. So what can you do now? You can give weights, very good. So what you could do is, well, in a sense, over here, you're giving it weights as well, and you're giving it an average weight. So basically what you're saying is that you've basically taken half of R plus half of P, okay? So you have weighted them. But the question is, even the weighting is not really solving the problem. So now, how can you solve this problem and make sure that somebody who has either R or P equal to 0, the final metric comes out to be 0? Okay, so but you see, accuracy wasn't changing in all of these cases. We saw that earlier. So now what we're saying is that if any one of them goes to 0, we want the output to be 0. How can you do that? It's very simple. What's multiplied by 0 is 0. Multiplication, right? So these are additions. You thought about addition, but what about multiplication? So what we could do is you could say a recall multiplied by precision and somehow divided by something. If this, now you can see that if you have any one of them being very dominant, okay? So you have something which is going left and right. If P comes out to be 0, this is going to be 0. If R comes out to be 0, it's going to be 0. So, you know, this seems to be perhaps more balanced in the sense you're looking for. Sorry? Yes, so each one balances. So you're saying that basically I want a multiplication. So think about this, whenever you have metrics, it's always good to have a multiplication, but it depends on exactly what you're looking for, okay? And again, you can think of a lot more metrics, and in fact, there are a lot more metrics, okay? We're just looking at some of the selected ones, and there are others, but I don't want to confuse you with all of them. So this is a multiplication technique, and this is called an F1 score, okay? Basically says, let's multiply precision and recall, okay? And at the bottom, we're going to do the sum. Okay, so I'm going to take the sum of precision plus recall. And so we multiply it by 2 as well, just for certain reasons. So let's take a look at this case. So we've got 4 cases, right? The first, third, and fourth were the balanced cases. The second one was the unbalanced case. The third and fourth differed because in this case, I moved the decision boundary to the left, okay? And in this case, I moved the decision threshold dt to the right, okay? So let's take a look at all of these parameters. Now, you could initially, let's just focus on the rectangles, okay? But ultimately, you've got to look at both of these because remember, in the first case, in the second case, where it was unbalanced, the numbers for rectangles were very good, okay? Both the precision and recall was very good. Even the accuracy was very good. But so if you just looked at the rectangles, it would be very good. However, if you looked at the triangles, then we remember that we were completely misclassifying the triangles, okay? Both the precision and the recall was coming out to be 0. This is a case where you had a very large number of rectangles and very few triangles, okay? Now, in this case, you could move the decision threshold to the left. And in this case, what you see is if you look at the F1 score, here the precision is going up, but the recall has gone down, okay? And in this case, when you move it to the right, and I'm just focusing on the rectangles, this goes up, but this comes down, okay? And you can see that if you look at the F1 score for the rectangles, then it can tell you how they're balanced, okay? So here, this is coming down a lot more as compared to the amount that the precision is coming down, okay? So then you would say, well, it seems that case 4 is actually better as far as the rectangles are concerned, simply because the impact on precision over here is not as much as the impact on recall over here. And so this would be preferred in this particular case, okay? Let's look at the triangle side. So in the triangle side, interestingly, because of the way the problem is somehow construed, is that the F1 score is not really changing, okay? Why is that? Because in this case, this goes down, okay? And this remains at 100%. In this case, this goes down. They're both going down by precisely the same amount. So it doesn't really matter. So if you were to choose between case 1, 3, and 4 for the balanced case, where would you put the decision threshold? Sorry? Case 4, right? Clearly it's case 4 because case 1 is the same as far as, if you look at the F1, the overall score, it's the same for the triangles. But for the rectangles, there is a difference. This one is clearly ruled out because this is a bad case. But here between these 3 cases, this one is performing the best. So it seems like case 4 would be the best in this particular case, okay? The case 3 has the most divergence in terms of F1 score. F1 and accuracy, yeah. So in F1, the score over here is you mean the difference between 50 and 80? In the so say that again. In the case 3, accuracy is 80%, right? And in right. So in terms of the overall accuracy, I'm not quite sure if I got your question because I'm finding it hard to hear you. Okay, accuracy and F1 score, okay. Right, but you see, the problem is that if you forget about this one, the case 2 is bad because F1 for this triangles is really bad, right? Now it remains between these three cases, and your question is that in this case, the accuracy in these two, the accuracy is actually improving. Okay, so these two seem to be better as compared to the case 1 where the decision tree is right in the middle. Okay, so moving the decision tree from the center seems to actually improve. Why? Because if you're looking at the overall accuracy, it's improving the overall accuracy. And in addition, it is, well, in some cases, actually reducing the F1 score. And in some cases, for the triangles, it's not changing the F1 score, right? So now the question is, do you go from here to here, or do you go from here to here? Okay. And between these two, it's clear that the F1 score over here for the rectangles is actually better for case 4. Whereas the accuracy is the same in both of these two cases. So I don't know if I've answered your question. Does that answer your question, that case 4 seems to be the best overall? Okay, yeah. Right. So accuracy by itself, I mean, it's as a rule of thumb, you will see accuracy being used. So in fact, in homework 4, you'll see that by one of the default measures, when you look at TensorFlow, they will show you the accuracy. Okay, but then you have to go into deeper. As a first level of metric, accuracy is a good starting point, but then you have to go into more details and to see are there issues with the F1 scores? Are there other issues? Okay. That's a good question. Whether once if you have the F1 scores, should you look at accuracy, or is that superseding the accuracy? That's a good question. I'll have to think about it. I think you can't leave it separately, because you see, if you look at the confusion matrix. Now, each one of these is looking at different things. So if you look at the accuracy, it's basically taking true positives and true negatives, and it's dividing over all 4. Okay. If you're looking at some of the other metrics, they will take some other column. All right. For example, one of the if you look at one of these, it will look at true positives divided by true positive plus false positive. Okay, and that would be the precision. If you're looking at this over here, or if you're looking at different angles, so each one of them will have its own uniqueness. So you can't really say that one of them is superseding the other. That's my understanding. Okay, but you could look at it a little bit further as well. But I don't think accuracy can be left out. So now the question is that I've taken some extreme cases, right? I've said, well, let's move it to the left, move it to the right, but how do you actually get the optimal value, right? It's not very clear. Do you just keep on moving it all across the board? How do you actually get the optimum solution? Okay, so can you think of a technique that would allow you to sort of optimize this? Now, think of all the optimum characteristics. Every time we try to optimize things, what were some of the techniques that we used to try to optimize things? Gradient descent, very good. So maybe gradient descent can be used, and maybe what we need to do is get an equation for sort of a solution that we're looking for, and try to find when is it optimal. Okay, so without going into too much detail, I'm going to show you something called the ROC curve. Okay, this is receiver operating characteristics. It's a big name. But basically what it does is it plots these two things. It plots what is called the true positive rate. Now, again, this is sort of like the recall. Okay, so here it's plotting the recall, right? The true positive divided by true positive plus false negatives. Okay, so this was the case where we're talking about recall true positive divided by false negative. Okay. So this is the recall. Then this is a false positive rate. This is not something which we've directly seen before, but basically this is now taking the false positives and dividing it, it's taking a look at these two. Okay. So as a result of this, and if you can work with this a little bit, but as a result of this, what you can do is as you move the decision threshold from one extreme to the other, what happens is that you get a complete set of results. Okay, so you can, in some cases, you'll get points over here, points here, points here, points here, and so on. And this is all happening because you're looking at different scenarios. Okay, and basically the idea is that you want to be able to maximize the area under the curve. Okay. So this is a technique which is used, and you will see this being applied also in your homework assignment, that I'll ask you to plot the ROC curve. And if you can imagine that if I looked at different curves, for example, this curve as compared to this curve, which one would be better? If you're trying to maximize the area under the curve, which curve is the dotted line better or is the red line better? Clearly it's the red line because it's got more area under the curve. Okay. I'm not going into all the theory. I'm just telling you what the conclusion is of the theory. Okay. Yeah. So if you're taking completely randomness, then what you'll get is this particular curve. I'm not again going into the theory, but this is what you will get. Sorry? Say that again. Yeah, so y is equal to x graph, exactly. So it comes out straight. But if you have something which is extremely good, okay, the perfect solution, and we look at some cases as well as we go forward, the perfect solution will be what? Guess what? It'll be right like this, right? So it will have the entire area under the curve. In other words, the area will be exactly 1. Okay. If it's looking at the triangle, it's exactly half. So the more this particular curve is shifted upwards, and you could get different curves. So you'll get, at times you'll get something, let me try to show you some examples. For example, you could get a curve which looks like this, and you could get a curve which looks something like this, okay? So these are different curves, but the question is which one is actually better? You simply take the actual area under the curve, okay? And whichever it has the greatest area, that generally is considered to be better, okay? And this is another technique. So all of these are different techniques which can be used to give you, to be able to decide which technique is better, okay? And which threshold could be better. Yes, Huda.
Sir, why are we maximizing the area under the curve?
Okay, as I said, I'm not going into too much of the theory. We'd have to spend a lot more time on this to be able to explain this. So I'm just telling you what the solution is. And this is a technique that is used, okay? But if you want, and if people are interested, maybe if you have time as you go forward, I'll spend a little bit more time in one of the other lectures to explain this, okay? But I want to skip this right now because I want to cover some other material as well. Okay, so if you want, just hold that thought and we can come back to it. So this is, in a nutshell, the different techniques that we talked about and different metrics. Okay, some of these metrics are kind of obvious. Some of these metrics are not so obvious. The ROC curve is not so obvious, okay? But we'll try to cover that later on as well. So let's take a look at some examples. Suppose that we're doing email classification, all right? And you have an example of a positive class being the spam. So you're trying to have, you're basically saying that if you have a lot of spams, then that's a positive class. So the question here is, which one of these is more critical? Which one of these criteria is more critical? So just let's look at the basic criteria. So false positives, this is when the actual email was not spam, but was predicted as spam, right? So false positive is that you're predicting as positive, but it wasn't actually a positive, okay? So the actual email was not spam, but was predicted as spam. And false negative is when the actual email was a spam, but predicted as not spam. Okay, so you're predicting it as negative, so it's in the bottom row, but in fact it was a spam. Okay, so now the question is, as a user of emails, which criteria would you want to emphasize? Which is more critical? False positive. So when you're saying that, but predicted as a spam, but it was not spam. Okay, so I think we would agree to that, because why is that? Can you explain why is that important? Yeah, exactly. So it was an important email, okay, but it was predicted as spam. And in fact, this has happened to me personally, as well as to a lot of IBA people. What used to happen is that we implemented the new email system. This was many years ago, and we got important emails which getting left out. I remember there was this one board of governors who sent out emails, and our, the secretary of the board of governors wasn't actually getting them. And our board of governors was furious. In the next meeting, they were like shouting at us. And we said, well, what's going on? And then we found out that it was actually in the spam folder. Okay, so this is an example of how one item could be a lot more critical than the others. Now look at the violence case. Positive is a false positive is when there is no violence. Okay, but it's predicted as violence. Okay, so you're predicting something as violence when in fact it is not violent. And false negative is when there was violence, but it was predicted as no violence. Okay, so here this was more important. False positive. Now what about in this case? False negative is clearly more important. Why? Because there was violence, and there's something going on, and you want to be able to detect that violence, but it wasn't caught. Okay, so clearly these are the two cases which become more important. So these are things that one has to think about when you're actually using these techniques. Right, so that now finishes the topic of metrics. Now I'd like to start the next major topic, which is decision trees. So these are different techniques that can be used for classification purposes and for machine learning. Okay, so now first question is, what are decision trees? We've seen trees before, okay, but we haven't seen them perhaps in the following manner. So let's take a look at this particular example. All right, so suppose that you need to decide whether to wait for a table at a restaurant, and this is directly coming out from your book. Okay, so in every tree you obviously have roots. Okay, you have a single root, sorry, and then you have leaves, which are the final leaves, okay, where you end, and points which are neither roots nor leaves are called branches or decision points. Okay, so you can see that all of these are where you're making decisions. Okay, and now the idea is simply to think about the kind of questions that you might want to decide. If you're a group of friends and you're going to a restaurant and you want to figure out whether you want to wait or not to wait, well, you might go through this. Okay, so for example, you might say, how many patrons are there? Is the restaurant empty, or are there some people there? If there's nobody there, then obviously it's not a very good restaurant. Okay, so you immediately decide, we're not going to wait, we're going somewhere else. Okay, now if there are some restaurants, okay, and and it's not full, okay, then clearly you want to go in there. Simple decision. Now the tricky part is that there are some people there, but the restaurant is also full, so it's probably a very popular restaurant. And now the question is, do you want to wait for it or not? Okay, this often happens when a new restaurant comes up in the city. So initially you ask the guy at the entrance, well, how long is the estimated wait? He says over an hour. Say, forget it, I'm not going to wait for over 60 minutes. He says 0 to 10 minutes, you say, great, okay, we'll just wait. Not very difficult. What if it's in the middle? If it's between 10 to 30 or 30 to 60, then you might want to think about it. Now, if it's 10 to 30, if it's under 30 minutes, you might say, well, am I hungry or not? In this case, I'll go down this path. In the other case, if I'll say, if I'm not really hungry, okay, sorry, if it's going on, well, sorry, over here we're saying that if there's an alternate available, okay, then if there's no alternate, then we might want to have. So what you can see is that it's complex, but this is the kind of decisions that one would have to take. Okay, so you can think of, for example, if you're hungry, if you're not hungry, you can wait for half an hour. If you're still hungry, If you're hungry, but if is an alternative available, if there's no alternative, then obviously you have to wait. Okay, and if it's raining, then obviously you're just going to go home and eat somewhere at home, right? But if it's not raining, then you might as well wait. So you can see there are different ways that you can construct trees, and you can think about, I often make these trees, even not having read all of this, in real life scenarios when you have real life decisions to make, like a family decision, right? Sometimes very important decisions. Then people get confused, right? If there are 5 people or 3 people or even 2 people arguing over the same thing, you might enter into a deadlock. But if you draw a decision tree and you even try to put probabilities in that, that's what I've actually realistically used with my family. My family is not all technical people, all right? So it's very easy to convince people. If you try to tell them, okay, these are the options, option A, B, and C, what is the probability of this, what is the probability of that, and so on. So you attack the problem very methodically, and you can actually get to a consensus between people who have very disparate views on life, okay? So think about this. Decision trees are very useful in general. So now let's take a look at a training scenario. Okay, so this was not a training. So this wasn't machine learning so far. This was simply a decision tree that was posed to you. Now, what if you have a lot of data, okay, and you want to be able to use the past data to be able to classify an object? Okay, so now this is a slightly different scenario. So suppose that you have medical data. Okay, so this is an example where, let's say you have data from a hospital, and you're trying to predict whether somebody has heart disease or not. Okay, and you have data about chest pain and something called, let's say, healthy circulation. Okay, if the person has good healthy blood circulation or not. Okay, so let's take a look at, you may have a lot of data. So in some cases you have no, and there is no heart disease. In other cases, you may have yes and yes. So you have a whole bunch of data, and these could be hundreds, even thousands of data points of thousands of different patients. And basically what you're trying to do is, based on this training data, you want to be able to, for a new patient or a bunch of new patients, if you're given whether this new patient has chest pain, yes or no, healthy circulation, yes or no, you want to be able to predict what is the best classification of this. Okay. Now think about the techniques that we've already used, and we've only used so far one technique, which is ANN or DNN. Okay, so how would you use a neural network if you had the same thing, and instead of using decision trees, you had to use a neural network to be able to do this? How would you use the training data to be able to come up with this decision? Right, very simple. So what you do is you could simply take a neural network, okay, and the output would be one of two, or it'd be heart disease, yes, and heart disease, no. Okay, when it's simply 2 cases, you can actually have a single output which gives you a probability between 0 and 1. Okay, so you don't need to. Yes, so it's quite possible that not always would you have the case. So for example, which case was this? This was this thing, right? So these are 2 different patients. Both of them were yes to both the questions. Though these are the features, right? So both the features were yes, and the output is different. Okay, and that's quite possible because these are different patients. But yes, so what you need to have is a lot of training data, and then you would need to see, well, what does the average, or what's the best way to predict it? Okay, and now we know that in a neural network, basically what you do is you'd give it 2 different parameters. Okay, so you'd give it chest pain, yes, no. You'd give it healthy circulation, yes, no. And you would give it to a whole bunch of neural network or deep neural network, and the output could be a single probability whether the person has heart disease or not. If it's above 0.5, then it's one category. If it's below 0.5, it's the other category. Okay. Now we're going to look at different techniques. So let's forget about ANN and DNN for a little while, for the next few lectures, and let's see if we can use a decision tree. Okay. So I'm going to take a simplistic version of the earlier case and try to show you how you can use a decision tree for this. Now, what we're going to do is, we've got these 2 features. We've got the chest pain and we've got the headache. And sorry, so I've changed this to make it even simpler. So instead of using the previous case, which was healthy circulation, let's look at headache. Okay. Now, most of us know headache has absolutely nothing to do with heart disease. That's why it's a simple case. So basically, I've said that there are 4 possible conditions. Let's make it simple. You have no, 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 yes, yes, no, and yes, yes. Okay. And I'm saying that it's kind of obvious that headache will have no impact on heart disease. Okay. And basically, I'm saying that in this case, there are only 4 data points available, and they're the obvious cases so that we can understand how to do decision trees. And what I'm saying is that when the person has chest pain, there's a 100% probability that they will have heart disease. Okay, very simple case. And headaches have absolutely no impact because you can see that yes, no, and it has no impact on the heart disease. Okay. So what we're going to do now is we're going to classify these as follows. Okay, the first thing we're going to do is look at chest pain. Okay, and we're going to fill this out. So let's say that initially, suppose you don't have all of this data. Okay, and let's take a look at the first case. It says chest pain, no. Okay, so it's false over here. And the heart disease is no. Okay, so this is 1 over here, 1 entry, because it's no, no. Okay, the second entry is chest pain, no, and heart and headache and heart disease, no as well. Okay, so in this case, it is again a 2 over here. So we get 2 over here. So far, so good. All right. The third case is now we're going to look at when it's true. So when chest pain is a yes, we're going down this path. Okay. And in both these cases, the heart disease is a yes. So we'll have 2 yeses over here and 0 no's over here. So is it clear how we're filling out the table? Okay. Now, similarly, if you look at the headache case, so you can see that it's going to be evenly distributed. Okay. Why is that? Because in the first case, it's no, no. Okay, that comes out over here. The second case is yes, no. So that comes out over here. Yes, no, yes, and a no. Okay. The third case is a no, yes. So that comes out over here and here, no, yes. And the fourth case is a yes, yes, which comes out over here. Okay. So, yeah. Yes, so we repeat, so what we're doing basically is we're repeating this whole exercise for first the chest pain case. Okay, so we're only looking at feature 1. Okay, and we're making this table for feature 1. We're making this simple tree for feature 1. Now we're making the same tree for feature 2, and we're neglecting feature 1 in this case. Okay, so this is a step-by-step process. I'm just explaining you what are the steps to be able to come to a decision tree. I haven't told you what the decision tree is, but I'm simply telling you what the steps. Okay, first step is you look at feature 1, you make this table over here. Okay, this part of a tree, and then you look at feature 2 and you make this table over here. Okay, once you have both of these, now the question is which one is better. Okay. Now, if you basically now the idea is that we want to be able to have as pure a bifurcation as possible. Okay. Now, if you think about it, it's kind of obvious if you look at the previous case that if you want to be able to decide between chest pain and headache, it's very clear intuitively that headache has absolutely no impact on heart disease. Okay, whether you have headache, everybody gets headache regardless of heart disease. But if you're having chest pain, then it's a very serious indicator of whether you have heart disease or not. Okay, and that's why if you have chest pain, then you have heart disease. If you don't have chest pain, then you don't have heart disease. It's a very pure data. Okay, so basically purity can be measured as follows, that if you look at your data, and if you look at this case, in the chest pain case, it's very pure groups. The subgroups that we've made are very pure. That in this case, if you have chest pain, then you have heart disease. If you don't have chest pain, you don't have heart disease, right? Very pure. And if you look at it, it's this case, right? On the other case, this is an example of impure groups, right? It's mixed. So if you have headaches, well, half of them are saying you can have heart disease. The other half are saying No, you don't have heart disease. Okay. Similarly, if you don't have headaches, it's the same problem. It's an impure group. Okay. So you can see that impurity can be reflected like this, that if you look at that particular subgroup, it's a mixture. Okay. It's all over the place. And if it's less impure, then it looks something like this. Okay. So this is how we looking at impurity versus purity. So basically what we want to do, the objective now is to be able to make subgroups. We're going to make a decision tree. Remember now the decision tree has got multiple levels. And at each level, we're going to ask different questions. The important thing now is that what should be the order of asking the questions, right? So over here, for example, if we use a decision tree which didn't have the right question at the top, it would result in impure groups, okay? But if you had a good decision tree, which resulted in subgroups which are very pure, it would be able to make, you'd be able to come up to a quick decision, okay? So for example, over here, you're saying weight estimate, you're saying, well, if the number of patrons, if there are no patrons over there, the restaurant is empty, you want to make a simple decision. It's kind of pure, okay? You just want to leave. So, so you want to have as pure groups as possible, okay? So if you look at this case, what would result in the purest group? Should we start by asking whether the person has a headache first, or should we ask whether the person has a chest pain first? Clearly, it should be chest pain because it will result in two very pure groups, okay? But it's not always that simple, right? In this case, it's kind of obvious, right? But it's not going to be always obvious. So you need to have a metric to be able to calculate which one of these should be our first question, okay? And there are various metrics. Now, one of the metrics is called Gini, okay? And this is the first example that we're going to use. The Gini index is fairly straightforward. There's also another one which is called entropy, okay? Let me discuss entropy first very briefly. I'm not going to go into the details of that, but does anybody remember what entropy was? If I say that entropy is very high versus very low, do you have some idea of what it means? How does it relate to randomness? If there's a lot of randomness, is entropy high or low as compared to no randomness? Okay, then you might have forgotten. Okay, it's very simple. More random things are, the higher the entropy. Okay, so kids, if you think of a bunch of kids in a classroom, they're going to be all over the place, right? So very, very high entropy. A bunch of adults, very low entropy. Why? Because they're all going to be very organized. They're going to be sitting quietly, and so you think about this example when you want to think about entropy. Kids, high entropy; adults, low entropy. Okay, so basically, one of the criteria is that you want to have. Now think about this: which one has high entropy? Which one has low entropy? Does this have high or does this have high entropy? Is impurity high entropy or is impurity low entropy? Is high, right? Because there's a lot of randomness. Okay, here there's no randomness, so there's low entropy. So one of the techniques, which I'm not going to go in detail, but just to let you know, is to be able to have subgroups in which the entropy is most or least, right? Because we want to have purity, so we want to have lowest entropy. However, I'm going to use a different index, which is called the Gini index. Okay, simply because it's a little easier to understand. So the Gini index does, if you have a binary classification, okay, if you have a question which is yes, no, remember this can't be applied in the first case where you had 3 questions, so, right? None, some, full, right? So I'm not looking at that. I'm looking at a very simple case where you simply have, yes, no, okay, true, false. So we're going to say 1 minus the probability of yes minus squared minus the probability of no squared. Okay, that's your Gini index. So let's see how this performs. Okay, so in this case, clearly in the chest pain case, if you ask the question, it's going to be 1 minus the probability of yes, which is 2 upon 2. Okay, 2 upon 2 minus the probability of a no, which is 0 upon 2. This comes out to be clearly 0 because 1 minus 2 upon 2 squared is 1 minus 1. So this comes out to be 0. Okay. So the entropy on the left side is 0. The entropy on the right side is also 0 because it's a completely pure. Okay. All negative no positive. So in this case, it's slightly different. It's 0.2 first and then 2 upon 2. Okay. But in both cases, the entropy comes out to be 0.0. Okay. Then what you need to do is do the average of both of these. Now, how are you going to do the average? In this case, you have two items on the left side and two items on the right side. The total number of items is 4. Okay. Total number of patients is 4. So if you do an average, weighted average, it's 2 upon 4 times 0 plus 2 upon 4 times 0. Okay. So it comes out to be 0. This is a very trivial case. Okay. So the average entropy at this level is also 0. Why? Because the entropy on both sides, even after being weighted, is coming out to be 0. So chest pain is very pure. It's coming out to be 0, the minimum entropy that you can imagine. You can't have less than that. Now let's look at the headache case. In the headache case, you have, it's pretty bad. The entropy is going to be high because it's 1 upon 2. The probability of a yes is 1 upon 2 here, squared, that's 0.25. And the probability of a no, again, is 1 upon half, squared, that's 0.25. And the sum, 1 minus this comes out to be 0.5 now. This is again high, okay? So it's sort of like the entropy as well. This is the higher it is, the worse it is. Okay, and in this case, again, because it's symmetric, it's also high on the other side. So the Gini on both of these is 0.5, and you do a weighted average over here. The Gini score is coming out to be 0.5 for this entire case. Okay, so basically what we're saying now is that if you look at both of these cases, this has a Gini score of 0. This has a Gini score of 0.5. So which one is better? Clearly, its chest pain is better. So whichever has the lower score, the Gini score, is going to be at the top, is going to be higher than the other. So in this case, the first one is going to be at the root of the tree, of the decision tree. So we're going to have the decision tree be very simple. We're going to put chest pain at the top. It has a Gini score of 0. Okay. Now the Gini score on both of these sides is already 0. So can you do better than that? You can't really do better than that. So is there any point in trying to have further questions? There's no point, right? Because chest pain can 100% tell you whether the person has heart disease or not. So there's no point in having further subtrees which ask you whether you have headache or not. Okay, so this was a very simple case. Now, if you understood the simple case, let's take a look at the original case, which is slightly more complex. Okay, this was the case where we had both of these cases with a different answer for both of these. Okay, as pointed out by one of you. So now let's do this again. So let's do the first one. First row, where does it go? No. Now we're looking at chest pain. So where would this go? It would come over here, right? So there's a 1 over here. The second case is a yes, yes. So it comes over here, right? Then there is a yes, no. Okay, yes and a no. So yes and a no here, right? And then there's a yes and a yes. And again, that comes out over here. Okay, so this is now no longer as simple as the previous case. So now what we're going to do, we're going to look at the second scenario. Okay, so now let's look at the healthy circulation case. So this is no longer a headache, it's healthy circulation. So let's fill this out. This is a no and a no. It comes out over here, 1. Yes and a yes, that comes out of 1 over here. Then a yes and a no. So yes and a no comes out 1 over here. And then a no and a yes. So that comes out over here. Okay. So as you can see that this is again going to have a high Gini score. Okay. So healthy circulation is actually not very good. It's not really telling you much. Sorry. It's sort of like the earlier case where it was like headache. Okay. But at least chest pain is a little better. So now we're going to do the Gini score. So let's do the Gini score over here. What is it going to be? 1 minus probability of yes. What's the probability of yes here? 2 upon 3, right? Squared minus 1 upon 3, the whole squared.
Sir, we cannot hear you.
Okay, let me see if there's a problem going on. There was some timeout, but hopefully now, let me know if you still can't hear me.
Yes, we can hear you
I
now.
can hear you now. Okay. So, so the Gini score comes out to be something like that. Here it's going to be 1 minus 0 squared minus 1 upon 1 squared, right? So if you look at the result over here, this is going to be 0. This comes out to be 0.44. So it's not as pure as before, okay? So this case is pure, but this case is impure, okay? And if you take the average of these two, so this is going to be 3 upon 4. There are 3 items over here, 3 cases, and 1 over here. So we're going to weight this by 1/4, and we're going to weight this by 3/4. The average comes out closer to be 0.44 rather than 0. Okay, so this is the overall score of chest pain. Okay, yeah. Yeah, if this is 100% pure, okay, and this is, so it's a relative term, okay. It could be 100% pure. It could be, you could say this is 100% impure in this case, okay. This is 100% impure because it's completely imbalanced. So now let's take a look at the healthy circulation. We can do the calculations again, but I won't bore you, but you can guess that it's going to be 0.5. Okay. Now, so the score over here is coming out to be 0.5. The score in the previous case was coming out to be 0.3, as compared to our perfect case example. I think the first example where it was 0 versus 0.5. Here it's 0.33 versus 0.5. Okay, so clearly we're going to use a chest pain at the top level. Okay, so now we're going to use chest pain at the top level over here. Okay, now the next question is, how do we actually do the next layer? Okay, now in the earlier case, the values, the Gini scores were coming out to be 0 on both sides, remember? Okay, and so we didn't have to go any further. Now here on the right side, it's coming out to be 0. So clearly this can be a leaf. You don't have to go any further. But on the left side, it's not 0. Okay, so now we need to go further and try to see whether asking the question whether there's healthy circulation, is that going to help or not? All right. Now it's a little tricky because now you have to look at only the cases which are falling on the left side. In other words, we're only going to look at the 3 cases where chest pain was true, and we're not going to look at the 1 case where chest pain was false. So there was 1 case where there was no chest pain, but there were 3 cases where there was chest pain. Okay. So now when we're going to recalculate the Gini of healthy circulation on the left side, but only by looking at the 3 cases which were relevant over here. Okay, is that clear? So we're going to recalculate it. Now let's recalculate it. So now we have to fill in this table again. Okay, let's take a look at this table. So now there are only 3 cases for this. So we look at the first case. It says yes and yes, that goes over here. Then we have a yes and a no. Okay, that goes here. And then we have a no and a yes, and that goes over here. Okay, so it's clear how we filled out the table for the 3 cases. Now let's calculate the Gini over here. So this is going to be half squared, right? And no is also half squared. This comes out to be 0.5. The Gini on the right is going to be 1 upon 1 and 0. So this is very pure. Okay, so this is coming out to 0. So this is on the left side, it's coming out to be 0.5. And on the right side, it's coming out to be 0. And now what we're going to do again is we're going to do the average score. Okay, now if you do the average of both of these, okay, which is done over here, it's 2/3 because there are 2 over here and there's only 1 item over here. It's 2/3 times 0.5 times 1/3 times 0. So the average comes out to be 1/3 or 0.33. So the overall average over here is 0.33. Okay, even though the average over here is 0.5. Now, if you compare it to the top level, okay, so basically what we're saying is that you might say that here the Gini is worse than the Gini over here. So why do we actually need to ask the question whether there's healthy circulation or not? The reason is that if you look at the average score over here, okay, it's actually doing better than before you ask that question. Okay, so this is important. Try to understand this, that before we ask the question whether there's healthy circulation or not, our Gini score was coming out to be 0.44, right? But when we did the analysis over here, we came out that on one side actually is doing really well. The purity is really well. So if you find out whether there is no heart disease, you are right on dot, and you can predict that the person does not have heart disease. Okay, sorry, this is the opposite. If it is false, in other words, the person does not have healthy circulation, then you can be absolutely sure that the person has heart disease. Okay, this has a Gini score of 0. So this on this side is good, but on this side it's 50-50. It's not really helping. Okay, question. So okay, so when will we actually use this? So the point is that, let's say, take a look at the full results and then get back to your question. So basically what we're saying is that over here, we started with chest pain. And if there was no chest pain, then it's 100% clear there's no heart disease. Okay. If there is chest pain, now it depends now further whether the person has a healthy circulation or not. Okay. If the person does not have healthy circulation, then again, there's 100% chance that the person has heart disease. Okay. But if the person does, the answer is true to this question, that do you have healthy circulation, and the answer is true, then you can't predict whether the person has heart disease or not. Okay. Why is that? Because this is equally probable. Okay. So now you can only say that if the person comes out to be over here, then you can't really be sure. Okay. Whether there's, in these two cases, the leaf will say there's no heart disease, there is heart disease. But here, the leaf will say, well, we're not really sure. Okay. So the classification could either be, in most cases, hopefully it's going to be slightly tilted on one side. Okay. It's not going to be right on the edge. So if it's slightly tilted on one side, the classification could be yes, heart disease or no heart disease. But if it's right smack in the middle, then it's not a good decision criteria. Okay. So one of the questions that you might be thinking of is that if you end up over here, why did we really need to ask? And this is my question to you. Was it really useful to ask the question, once you're over here, was it really useful to ask the question that the person has healthy circulation or not? Did we add any value? If you're at this point, could we have skipped this question? You're saying, no, we shouldn't have skipped it. We should have asked this question. Why? Yeah, exactly. So because if both of these were 0.5, if the average score over here was worse than 0.44, then it would have been, then what we would have done is we would have made this a leaf node. But because the average score, the Gini score is coming out to 0.33, and why is that? Because it's the average, the weighted average of 0 and 0.5. In one case, we have a very good predictability. And so because of that one case, the average score is coming out to be lower than the score above. And so there is some utility to actually going down that tree path. Okay. Even though in one of those leaves, it may end up with not a very useful scenario. So you can see how now you can construct a complete detailed decision tree. And all you have to do is you have to construct you have to use some criteria, whether it's the Gini score or whether it's entropy. Entropy involves logarithms and so on, it's a little bit more complex. But generally, in fact, I think most people either use one or the other. Okay. I don't know if one is preferred over the other. But this is basically what decision trees are. Okay. So now the question now remains that how do you actually use it? So hopefully now it's very clear how one would use it. So basically what you would say is that you would use the training data to be able to create your decision tree. Okay. Once you've created your decision tree based on all the training data, then a new patient comes in, you'd ask the same questions. Okay, does the new patient have chest pain? Yes, no. Okay, and hopefully after answering each one of those questions, you would get to one of the leaves, and that leaf would tell you what the decision is, how to classify that person. Okay, so that's all that decision trees are. And if you think about it, as compared to neural networks, what do you think are the advantages of a decision tree as compared to a neural network? You think it has some pros and cons? Yeah. Okay, very good. Good observation. Basically, your observation is basically saying is that for the given amount of data, it will do a very accurate job. Okay, because remember in neural networks, you had weights and they had to be trained on a lot of data, right? Now imagine in this particular case, I only have 4 items, but based on these 4 items, I can do a very accurate very accurate classification. Now imagine if I had to do this with neural networks, the weights after training with these 4 data points still may not be very good, okay, and still might be doing really bad. So you need to have a lot of data in neural networks. But can you think of some other advantages and disadvantages? Explainable. Remember, neural networks, the big problem was that you had an answer, but you couldn't explain why. So you had an answer, but if somebody asked you why, did you have an answer? Now over here, can you answer the question why? Very easy to answer, right? Because you're simply going down very straightforward questions, very intuitive, humanly understandable. So if a doctor looks at it, he'll say, okay, I like this because I can see why you're coming up with this decision. Why? Because you asked the first question, then you asked the next question, and so on, and finally you came up with an answer. That's how actually doctors work. They don't actually mentally, perhaps don't work with the decision tree, but internally they've sort of made their own decision trees. But if you ever work with a doctor, recommend decision tree, okay? It'll be easily understandable. But there's still some problems. What do you think could be a possible problem with this? Now, think about the issue of overfitting. Do you think this will be better at this will overfit or not? Well, it's not obvious, so I'll tell you the answer. This has the problem of overfitting, okay? If you train it on a lot of data, then it may take up some peculiarities of the data and come up with an answer which is only true for that particular set of scenarios, okay? And if you slightly try to give it a different type of scenario, it may come up with a completely wrong answer. So it does overfit, okay? So now the next question is, and we're sort of going over time, but I think we have a few minutes left. So let's try to see, can you think of a way of try to generalize the results? Now remember, in neural networks, I gave you ideas of how to generalize. Okay, we said use dropout, dropping things. What other techniques did we use to generalize? We use some other techniques as well, right? We talked about when we're looking at the loss, we looked at the training versus the test loss. And then when the test loss starts to go up, we stop, we say we're not going to overfit. Okay, this is where so can you think of other techniques over here? Can we use the same techniques over here or not? Can we avoid overfitting in this? Can we sort of go to the right and say, well, we're going to stop when the training and the test data starts to diverge? Perhaps you could do that, okay? So we could do is, let's take 80%. So you have a lot of data. You have thousands of data. You take 80% of that data and you take 20% of it to be test data, okay? And you could repeat the same thing. So you do the analysis, you see the results, and you see whether the training and testing is diverging or not. Okay, that's one technique. Now, another technique which we haven't talked about is something called ensembling, okay? So ensembling basically says is that we're going to take, and this is true for a lot of other cases, it's not really only valid for decision tree. Basically, what it says is that can you take more models and take the results, and is it better than fewer models? So the question that we're asking is, are more models better than fewer models? Okay, so let's say that you take some results versus you take a lot of results. Okay, it's not necessarily the amount of data. So the amount of data is fixed. Okay, so I'm just going to tell you what ensembling is, so that it sort of explains what we're going to do. So what basically we're going to do is we're going to take the same amount of data, but this is a technique called bagging. Okay, what it does is it converts that into smaller subsets of data. Okay, so let's say you have 1,000 records. You randomly pick 100 records randomly. Okay, then you pick another 100 records, but they can be from the same one as well. So you're taking the 100 ones, but you're putting them back in. Okay, and you're taking another 101 from the original 1,000. You take another 100 records from the original 1,000. So now, because each one of these is being independently picked, they're all independent of each other. Their results are not going to be correlated. Okay, so you pick a whole bunch of these, and you take each one of those, and you create a tree out of that sample. Okay, so here you get one tree. This is based on one subset of the original data. Now you're going to make the entire tree. Okay, you're going to use that, and you're going to train it based on all those 100 points, or it could be a large number of points, and you train the data, and this will give you a particular answer, right? So you come up with a new scenario, new patient. You've created now hundreds of trees based on hundreds of subsets of the original data, but each one of them being randomly selected. So now they're not correlated. So what you're going to do is you're going to take the new data. So you have a new patient, and you ask the first tree, what class is it? Okay, so he says this is the red class, whatever that is. Okay, the other tree says no, this is supposed to be in the blue. So this is, let's say, an apples and oranges. So he says it's supposed to be an apple. This says it's an orange. This says an apple, orange. What are we going to do? Apple, right? Because we're going to simply take a vote of all the trees, and we're going to go by the majority votes. Okay, so you can see that the random forest is basically what this is doing. This is what I've just explained. You create smaller data sets, and these are called bootstraps. Okay, using sampling with replacement. Okay, so each one of these is independent of the other. You create trees using random subsets. Okay, for a new patient, apply the attributes to each tree and note the result, and then take a vote on the most popular classification. Okay, fairly straightforward. Now, final question before we stop. Yeah, question.
Sir, wouldn't the entropy of such a data set be high?
Okay, so that's an interesting question. And what you're saying is that would the entropy be high of the data set? Sorry? Okay, so the point is that the entropy, we're not really looking at the entropy. What we're doing is we've picked a random sample, and now we're creating a tree out of that. Okay, the tree will ensure that the entropy or the Gini score is minimized in all the subgroups that are formed. Okay, so ultimately each one of these trees is going to try to minimize the entropy of each one of those subgroups. Okay, does that answer your question? So we're not looking at the entropy of the entire subset of data, but we're looking at the entropy of the subgroups of the tree. Okay, slight difference. And each one of them is going to come up with their own subtree. One of the things I didn't mention is that create trees using a random subset of attributes. Okay, so I missed this part. What you're also going to do is, for example, you have a lot of features, right? Feature 1, feature 2, feature 3, feature 100. Now, because you're creating a subset of that data set, not only will you take a subset of that data set, all right, you're going to take some portion of that data, but you're also going to get a subset of the features. So you're not going to train that on all the features. Okay, you're going to train it on a subset of the features. Okay. Yeah, so you're not going to classify all the features. So for example, if you had a lot of features over here, in this case, we've only got 2 features, right? Chest pain and healthy circulation. Suppose you had 10 other features over here. So when we're creating the random forest, we're only going to select for each forest, it's going to be random in 2 ways. It's going to be a subset of the data, plus it's also going to only make a tree based on a subset of the features. A random generation of the features as well. Okay, so it's a double randomization, and that's why it's called a random forest. Okay, this is really random. And so coming back to the final pros and cons, what are the pros and what are the cons? Now, if you think about the random forest, now it's got the results of a large number of trees. So do you think it's going to be more accurate or less accurate than a single tree? It's hopefully going to be more accurate. Okay, so one of the pros is that it's going to be more accurate. Okay. So sorry, earlier in the single tree decision tree, you would actually use the entire data set. You're not going to make subsets. You're going to use the entire data set and come up with a single decision. And you're going to use all the features. So the question is that better, or is to be able to break it down into a random forest, and is that better? So it's perhaps more accurate, but what about the issue of, in terms of overfitting? Do you think this will be more generalized, or the earlier case was more generalized? This would be more generalized because you not only you perhaps may not even be using the entire data set, because you're using, so if you're looking at a large data, you may actually at the end of it, you may not even have used 100% of all the data because you're randomly selecting. And in addition, you may not have used 100% of all the features. So it's sort of generalizing the result. It's avoiding overfitting. But what is one of the major cons? So if you think about what is one of the major advantages of decision tree, of a single decision tree as compared to the neural networks, what do the doctors like? It's explainable, right? Now what's happened? Is it still explainable? It's not explainable because now you don't know, you're looking at hundreds of different decision trees. Each one of them is different and simply giving the average. Now the doctor is again going to be confused. He's going to say, what is this based on? Okay, so there's no pleasing some people. So that's it for now. This is the reasons more accurate, avoids overfitting, but less explainable.